Hi friend. So today we are going to talk about Menten's equation. So it's a very important topic if you are preparing for CSR Net, Life Science, DBT, ICMR or GATE Biotechnology. So for all this exam and also for interview, this question always comes related to Michaelis Menten's equation. So what is this equation about and how it is related to enzyme kinetic? This is what I'm going to talk about in this video. So please make sure to like, share and subscribe this channel. So before going into this equation, talk about what are enzymes and how do they work. So if you know the conversion of a substrate to a product, right? So their substrate get converted to the product by the action of an enzyme. So the substrate can be directly converted to product as well, but this without the enzyme, this is very slow reaction. So enzyme comes and they made this reaction faster by reducing the activation energy. And when substrate is there, and how does the enzyme cause this reaction is by different mm, equation. So suppose you have a substrate, right? And then an enzyme comes. So this enzyme binds to the substrate and forms a complex which is called ES complex. So this is the complex like the formation of enzyme plus substrate complex. And then this complex get converted to the product and the enzyme is released. So the enzymes are never used in this reaction. They are always released to bind to another substrate and then continue this reaction. So this reaction goes forward. So we can say this is the first reaction, the formation of enzyme and substrate complex. And then this is from the enzyme substrate, the reaction is the formation of the product. So this reaction can also goes backward in which this enzyme substrate complex, it can either go to form the product or it dissociate and forms the substrate itself again. And then this process from product and enzyme, this can also occurs in the backward reaction. So from here you can see this part, the first reaction where the substrate and enzyme forms the enzyme complex. So the rate of the reaction, which I am going to say rate 1, it is the constant, the rate constant which depends on the different environmental condition and the concentration of enzyme and the concentration of substrate. So the how this reaction proceed depends on the concentration of substrate and the enzyme. And then we have the second reaction which is rate 2, which depends on the K2, the rate constant for this reaction, and also depend on the concentration of enzyme substrate complex. So in this reaction the E remain constant. So suppose the enzyme is constant. Okay. So if the enzyme is constant and so if suppose you have 5 enzyme and each enzyme can bind only to substrate. So in total all the enzymes can bind 10 substrate. So I am plotting this graph which is against rate, the speed of the reaction and the substrate. So if we consider that the enzyme is constant, so what happens? So as the substrate increase, the rate of the reaction to form these and these will also increase. But there comes a point when all the enzymes is bound with the substrate because 5 enzyme, 10 substrate, and suppose we reach 10 here and now we increase further. So the enzyme cannot bind more substrates. So what happens? It goes to a place where it becomes saturated. So all the enzyme becomes saturated and this point is called the Vmax, the maximum speed of the reaction at which all the enzymes become saturated. So now you understand what is the basic enzyme like concept, like the formation of the ES complex and then depends formation of the product that depends on the concentration of all these factor, and at the higher concentration of substrate the enzyme becomes saturated and reached a point which is called Vmax. So now we are going to talk about the Michaelis Menten's equation. So before going that, there are some assumptions that we need to consider which are called steady state assumptions, okay, which we need to consider before going to the Michaelis Menten's equation. So I will write that equation again, which we wrote substrate plus enzyme. The first one which will give you the ES complex, and then the P plus E complex by the second reaction, right? And then we talked about that it can go in the reverse phase as well. So we assume that this is -1 because this is going in the reverse phase, and this one as -2 because it's also going in the another way. So what is the assumption is that the ES complex remains in equilibrium. What does that mean is formation of this complex is equal to the dissociation of this complex. Okay. So if you look at this reaction, how this ES is formed? By E1, right? Rate of 1 plus when these product and enzyme goes back to the ES, so rate of -2, right, which is equal to the dissociation, and dissociation as you can see is when ES either goes in this direction or is in this direction, which is rate -1 plus rate 2, right? So if the assumption is that, so this point, the -2, the rate -2, it happens very rarely because if you know the conversion of substrate to product using enzymes, it's basically a thermodynamically stable process. So the product that is formed in the end is more thermodynamically stable than as compared to the substrate. So the movement back here is very rare because once it reaches a thermodynamically stable state, it don't want to go to a state which is less thermodynamically stable. So this process occurs very rare as compared to the rate 1. So what we can write is rate 1 is equal to rate -1 plus rate 2, because this is very thermodynamically unstable and very negligible if it happens as compared to rate 1. So it approximately equals to this. So now what is rate 1? It's this, right? We can write K1 ES is equal to, what is rate -1? Is the dissociation to substrate and enzyme, and the rate, it depends on the ES. So what we can write is this plus, what is rate 2? It's the formation of product using ES. So it's K2 and it also depends on the ES. Okay. So now what we have is, as I told you, this one, and then the total enzyme. What is total enzyme? It's the enzyme that is bound to the substrate or the free enzyme, right? Because the enzyme can occur either in the free enzyme form or in the enzyme substrate complex. So what we can calculate, simplify, is the free enzyme, and what the equation we get is this one. And now we can put this equation here in the K1, and what we get is K1, I hope you can follow it, K1 is equal to, K1, and then I can put this reaction where it's in Et, right, minus Es, and then we have still the substrate, so I can put it in inverted commas, and then we have K minus 1 Es plus K2 and Es. Okay, and now what we can do from here is we can take the Es in common, and what we get is K minus 1 plus K2, right? And then here we can multiply this. So what we can do is we can put this K1 here, and then what we get is Et minus Es, and then the substrate here is equal to Es, and then what we have is K minus 1 plus K2 and then K1. Okay, and this is what is called the Michaelis Menten constant. So what it is called, K minus 1 plus K2 upon K1 is called Km, which is Michaelis Menten constant. So I will talk about it in detail after deriving this equation, what is Km and everything. So now we continue this. So here what you can do is you multiply this with this, so it comes ETS minus ES and S, and here we can put simply as ES with Km. And now we can move this equation here, ETS, and then if we move it here, ES Km, so this equation goes here plus ESS, and then we can simplify it further. We can take ES in common, and what we get is Km plus S. Okay, and here we have Et and S. So now we can simplify it further, where we can put these here up downstairs, like on the denominator. So we get ES is equal to ET S and Km plus S, right? And so now what we need to think. So we have talked about the V naught in the first place when I was describing you what are enzymes, and we talk about this is the rate of the reaction of formation of product, right? dP by dt, which we can also write as K2ES, right? Because the K2 is the formation of the product from the enzyme substrate complex, and this is what we are talking about. So suppose, like the assumption that we take, that at the very high concentration of substrate all the enzymes will be saturated, right? If the substrate concentration is too high, all the enzyme will be bound to the substrate. Like I have talked about, if we have 10 substrate and 5 enzyme, and everything will be bound, and we reach the stage where V naught is equal to the Vmax. If you remember the first graph where I have talked about where everything gets saturated, right? This is Vmax, and this is the substrate, the very high concentration. In that case, V naught become K2 ET, right? Right, you agree, right? And then what we can do here is we can put this equation here, because we say that Et is equal to Es. So V naught become K2 ETS and then Km plus S, and this is what is Vmax, right? because I have talked about V naught is equal to K2 ES, right? And but if we reach a place where it's super saturated, E2 become ES. So this becomes Vmax, right? And then Km plus S. So this is our Michaelis Menten equation. Okay, this is what Michaelis Menten equation, where it says the V naught is equal to Vmax, the maximum concentration, divided by substrate, multiplied by substrate, and Michaelis constant plus substrate. So you will be thinking, what is Michaelis constant? What is K? So just bear with me for a bit more. So imagine Km is equal to substrate. Okay, just imagine that if Km is equal to substrate, what does V naught become? Vmax, right? And then S, and Km we are saying if it's equal to substrate, it becomes Vmax S, and which is Vmax by 2. Okay, so what we are saying is, if so Km is the concentration of substrate where V naught is equal to half of Vmax. Like this video, please don't forget to like, share and subscribe my channel. Thank you. And if you have any doubt, please let me know in the comment section.